Hello, everybody. Welcome back to Markov processes. Um, I have a lot to get done today, so I don't really have time for questions on the homework right now, but I will try to end early and I can certainly stay as late as you need at the end. And the reason is because we have an exam coming up and I I need to get to a good break point. And I'm also holding back your current homework because I'm not sure which problems you can solve yet. And yes, there is a current homework, but there will not be one the week after the exam. It will help you review, and I will make sure it's not extra challenging, which I think it was last time. So you guys couldn't get to the review problems because you spent all your time on the homework, but I'll make sure it's really productive for your review. So homework's coming out later today, and we have no class next week. I will be around and answering my emails during the week. So there, I am going to share my screen. We were talking about birth processes, and today I want to talk about birth and death processes. And when you add death to the mix, it's a little morbid, but because you can go up and down with your Markov process, we can potentially reach an equilibrium and have some stability and get to talk about stationary distributions. So here's where I think it gets interesting again. So before we launch into the birth and death process, I mentioned last time this idea about for a continuous time Markov chain on a discrete state space, the times between events are actually necessarily exponential. And we did get that for the Poisson process, but the Poisson process had a lot of stuff in it, a lot of structure. We had I, double I, and triple I. But for a birth and death process or a more generic Markov process, we don't necessarily have all that additional structure about independence. So this is actually for any continuous time Markov chain on a discrete state space. So I'm going to let x of t be a continuous time Markov chain on a discrete state space. Doesn't have to be integers, certainly doesn't have to be positive integers, although that's what it's been for us. So the inter-event times, and I'll be a little more specific about this in the proof. I'm going to define what is known as a holding time. The inter-event times are necessarily exponential, so must be exponential. And that's coming out of seemingly nowhere. Well, not nowhere. It's Markov. It's coming out of the Markov assumption and the kind of short range memory of a Markov process. It's not exactly true. Everything's dependent on everything before, but once you know the time step just before, you don't need the previous information. So let's prove this. So suppose we have a continuous time Markov chain, and I am going to start out by supposing we're in some state I. So suppose we're currently in some state I, and what is currently? I'm going to make currently times 0 by time homogeneity. So by our assumed time homogeneity, let's call now time 0. Okay, so we're currently in some state I, and I'm calling now time 0. So I'm going to let t sub I be a random time, and this is going to be the time until the first move away from state I. And you do have to move away. So if you have some sort of process where you can stay flat, it's unlikely for a continuous time Markov chain, but maybe you could make some sort of transition and stay where you are somehow. But here we actually have to move away. So it's the time until we first move away from state I. And this is, I'm going to sneak a definition right into the middle of my proof. This TI is called a holding time. Just for the record. So we're kind of holding in one state. And so what we're going to do, we want to prove that this is exponential. And so we're going to prove the lack of memory property, because we did show that for continuous random variables, the exponential is the only distribution with the lack of memory property. So we're going to show lack of memory. And then I'm a little lazy to write this, but recall that the exponential distribution is the only continuous distribution with this property. So if we can show that this continuous random variable ti has the lack of memory property, it must be exponential. Okay, so to do this, I'm going to take a couple of time points, s and t, greater than or equal to 0. Let's say strictly, although it's not going to really matter. Okay, more specifically, let's say s is greater than or equal to 0 and t is strictly greater than 0. So I want to consider the probability that this holding time in state I is greater than s plus t, given this holding time is greater than s. We want to do a computation, and we want to get down to the probability that the holding time is greater than t units, that the fact that we've already weighted s units does not matter. That's the lack of memory property. And if we can show that, then ti must be exponential. So let's show it. The first thing I want to do is translate this probability here into the Markov process. This is going to be like the continuous stuff, the given stuff. We are starting in state I, although I don't know, I don't really want to mess this up with like I subscripts. So everything I'm about to do is conditioned on the fact that we started in state I. And so the event that ti is greater than s, this means by time s, we still have not moved away from I. So in terms of the chain, this is the same thing as saying x of some time u equals I for all u between 0 and s. So we start at I and we're at I for all times between 0 and s. And that means that we did not leave I before time s, and that means that the holding time is greater than s. And then on the left-hand side, it's going to be similar. The event that ti is greater than s plus t is the same thing as saying that the chain is still in state I for all u between 0 and s plus t. Sorry, I couldn't really fit it. So that's the translation of the ti stuff into the Markov chain stuff. Now, we're already given that we're in state I for all u between 0 and s, and so we have some overlap here, a little bit of redundancy. So I can take that away and say this is the same thing as the probability that the process is in state I for all u between strictly greater than s and less than or equal to s plus t, given the same thing we were given before. Okay, so by the Markov property, I actually don't care about all this time. I only care about the most recent time step, which is going to be s here. So by the Markov property, this is the probability that x of u equals I for all s less than u less than or equal to s plus t, given that x at time s equals I. And by time homogeneity, so I don't use those initials very much, this th here is time homogeneity. I can have s be anywhere. So I'm going to let s be 0, or if it's not, I'm going to slide this down to starting at 0. And so when s is 0, I get the probability that xu is I for all u greater than 0 and less than or equal to t, given x at time 0 equals I. So here we are again, starting in I, and we know if we're looking at time u, we are still in I for all u up to and including time t. And that tells us we have not yet left I. And that's the same thing as saying that the holding time in state I is more than t units of time. And that's what we wanted to show. So we have our lack of memory property. We showed that the holding time Ti satisfies this thing is equal to this thing. So lack of memory holds, and this implies that Ti must be exponential or have an exponential distribution. I don't know the rate, but some exponential. And we are done with this proof. Okay, so sometimes if you're reading, Markov books or articles, and you suddenly see people assuming something is exponential when that wasn't given, it's probably something like this going on. So this probability says we're starting at I, that's like here on the graph, and then we're staying in I for all times between 0 and t. And so eventually we're going to move away from I, but I don't know when. All I know is that it didn't happen in here. The first time we moved away from I is greater than t units of time. Yeah, so again, I was too lazy to write why we were showing lack of memory, but this implies we must be dealing with the exponential distribution. And so as a very quick example, let's go back and look at our first very quick linear birth process or Yule process. So this had birth rates. We called them lambda I, which is supposed to be the rate of increasing the population by one individual at the time when the population size is currently I. And we showed that this was I times lambda. And what's happening here is that each individual could give birth in a tiny interval of length h, as h is tending to 0, with probability lambda h plus some negligible stuff. And that is what's happening is that the individuals are actually taking an exponential amount of time with rate lambda to give birth. And then if there's currently I people in the population, the birth rate represents not the next birth for an individual, but for the overall population. And so you have I people in the population and they're all racing to give birth. So you have I exponentials with rate lambda, and the time of the next birth is the minimum of those. And the minimum of I exponentials with rate lambda is exponential with rate I times lambda. So that sort of jives with what we know. So that's pretty cool. Okay, so let's introduce death into the equation. Here is a definition for you of a birth and death process. So a stochastic process, x of t, collection of random variables for all t greater than or equal to 0, is a birth and death process. I think you probably know what I'm about to say. Population can go down as well as up. So birth and death process, if this xt is a Markov process, just like with the birth process, we're not getting Markovness out of some axioms like I, double I, triple I. This is assumed. You have to have a Markov process to make a birth and death process. So if it's a Markov process on the state space of non-negative integers, you can think of this as a population size, such that, so I'm going to put all those little o statements into one here. Let's talk about the probability that x of t plus h minus x of t is 1 or -1 or 0 or greater than or equal to 2. So in general, I'm going to put equals k. Given the current population size is I. Now, if k is 1, this represents a birth. And we're going to get a birth rate, lambda I times h plus little o of h in the case that k is 1. And if k is -1, it's going to represent a death. And the death rates are usually denoted by mu I. So I'll define that at the end. mu IH plus little o of h. This is the rate of going down by 1. We'll have probability little o of h to have a change in k that is in absolute value greater than or equal to 2. So we can't go up or down by 2 or more. And then the rest of the probability, 1 minus lambda I plus mu I h plus little o of h when k is 0. So all we've done is we've added this, and that changes this one because they all have to add up to 1. Other than that, it's pretty much the same as a birth process. And the lambda I are the birth rates. In particular, it is the rate of birth at the instant the population is at size I, and mu I here are known as the death rates. And these should be non-negative parameters. So that's the definition of a birth and death process. So let's look at an example of showing that something is a birth and death process. So I have a population in which no one gives birth. We are going to allow this population to increase through immigration. And so suppose that we have immigration according to a Poisson process with rate lambda. So that's a constant arrival rate. It's not like each individual has their own Poisson process. Okay, so it's not like each individual is racing to bring in an immigrant. There's just a constant stream coming in from the outside. And so the lambda is not going to depend on I. And we should see in the end that the birth rate at the instant when there are I people in the population, we're going to see that it's this constant lambda. We're going to go through the math and figure that out. Okay, and then suppose that the death rate per individual is some mu greater than 0. And when people in stochastic processes write that, they mean something pretty specific. So i.e., the probability any individual in this population dies in a very small time interval starting at t and going up to some t plus h, and t is going to be vanishing, we're going to be letting it go to 0, is proportional to the length of that interval using this rate mu times h plus little o of h. This is not, although it's not exactly what we showed in the theorem, this statement alone implies that the next death happens after an exponential amount of time with rate mu. Let me show that later. Let's just leave that out and get to the birth process. So these two streams or event streams have to be independent, at least in this example. And I'm going to let x of t be the population size at time t. So I want to check that this is a birth and death process and give the birth and death rates. So we have a few things to look at. First, I'm going to look at the probability that we have in an interval from t to t plus h that we have an increase of size 1 when the population size is currently at I. And there's many ways this can happen now because we have births and deaths. So most of them are going to go away, but this is the probability of exactly 1 immigration and 0 deaths in the interval from t to t plus h, given that x of t is I, plus the probability of exactly 2 immigrations, I can't read that, and 1 death in t to t plus h, given xt equals I, plus dot, dot, dot. But the immigration stream is Poisson. And so we know we can't get two immigrations in this tiny interval with any, that probability is negligible. So all of these probabilities are going to go into the little o of h part, except for the very first line. The immigration stream and the death stream are independent. So I get to multiply this probability and this probability all in that conditional land. So what is the probability we have exactly one immigration in an interval of length h? That is a Poisson number that is a Poisson distribution with parameter lambda times h. So this is e to the minus lambda h to the 1 over 1 factorial. So that's just using the fact that we're looking at an interval of length h and we're waiting for an arrival from a Poisson process. Times the independent death thing. So out of I individuals, we have to choose 0 to die. Sounds weird. Each one will die in this interval of length t of length h with probability mu h plus little o of h. So we get that to the 0 power, and then the rest of the individuals, like we're choosing 0 to die and the rest to not die. So the rest of the probability to the I minus 0. Okay, so the next line, if you broke this up into immigration stuff times death stuff, the probability of having two arrivals in the Poisson process in that tiny time interval is little o of h. We showed that, but if you don't remember that, then you can write out this sort of thing with 2's in places of the 1's and work that out, and it will turn out to be little o of h. So remember, in the Poisson process, we defined the probability of having being greater than or equal to 2 as little o of h, but then later I showed you why this implied that the probability of having exactly 2 or exactly 3 arrivals is little o of h. We showed that way back now, it seems. Okay, so I'm just going to finish this second line. 0, exactly 1 death. Out of the I people, we have to choose 1 to die. We get the death probability for that interval for one of the people, and we get 1 minus that death probability for the rest of the people, plus ... But we have a little o of h function, and nothing here is going to ruin that. We don't have any like divided by h things where we might actually knock out the little o of h-ness. So everything here, if you were to expand that, is either a constant, so a constant times little o of h is still little o of h, or is little o of h itself. And little o of h times little o of h is still little o of h. So this entire line, little o of h is out. Little o's out of h. Goes away, is negligible. Same thing with the next line. So I am going to rewrite the first line. I have lambda h from here, and I'm going to start simplifying. So we know that the e to the negative lambda h out front is 1 minus lambda h plus little o of h by a Taylor series expansion for e. So this term became this term. I choose 0 is 1. This mu h plus little o of h to the 0 is 1. We have the rest of this stuff to the I, and we showed last time that that is equivalent to 1 minus I mu h plus little o of h. And I believe that's, you just did that on your homework or something like that. So we had 3 computations like this, and I will collect them for you and put them on the review sheet. By the way, you don't get to bring anything to the exam, but I will be providing some things like these formulas. And when I give you the review problems later this week, I will also give you the cheat sheet so you'll know exactly what you'll have. Okay, plus all the rest of the stuff, little o of h. So yeah, lambda h times 1 times this other one, that gives us lambda h. When you multiply lambda h times lambda h, that has an h squared, that's little o of h. And when you multiply that by 1, it's still little o of h. And if you follow all the other terms through, like lambda h times a little o of h term is still little o of h. And lambda h times I mu h has an h squared in it, and that's little o of h. So everything else, little o's away. And we started with I people in the population, and we got it into the form lambda I h plus little o of h, where lambda I is just the constant lambda, no matter what I is. So that's the birth rate in the population when there's currently I people in the population. And as we said at the beginning, it's constant because we just have this constant Poisson stream coming in. So we're not too surprised. So there are four things to show a birth and death process. There were four things, and three of which we need to show, and the last one is locked in, 3 probabilities. I'm only going to do one more in the interest of time. So let's look at the probability that in this interval of length h, we decrease by 1, given there's currently I people in the population. So this could mean that we have 0 immigrations into the population and 1 death. This is in t to t plus h, and this is given that x of t is I. Or we can have 1 immigration and 2 deaths in there, or, and we can keep adding these up. Plus dot, dot, dot. So because the immigration stream is independent of the death stream, we can take the first probability, say, and break it up into the probability of 0 immigrations and the probability of 1 death and multiply. So 0 immigrations in an interval of length h, the number of immigrations is Poisson with parameter lambda times h. So we get e to the minus lambda h to the 0 over 0 factorial. If you were taking the exam and you just wrote e to the minus lambda h, that's fine. I know what happened to your other terms. I just want to make sure you know. 1 death, when there's currently I people, out of I, we have to choose 1 to die. The death probability in this little interval is mu h plus little o of h. We get that for 1 person, and we get 1 minus that probability for the remaining I minus 1 people. Do we know the other stuff is little o of h? I do know past here, when I get to 2 immigrations and 3 immigrations, that is little o of h because that's a Poisson process, and the probability of 2 or more arrivals is little o of h. I suspect the same thing is going on with deaths, but to be sure, let's write another line here. So 1 immigration in an interval of length h is e to the minus lambda h to the 1 over 1 factorial. 2 deaths means out of I people, we have to choose 2. We get the death probability, mu h plus little o of h squared, and the rest of the probability to the I minus 2. And then the other terms are little o of h, just because we can't have 2 or more arrivals from the Poisson process in the tiny interval. Okay, so let's simplify this. For the first line, this goes away and this goes away, and that e will simplify into 1 minus lambda h plus little o of h. The I choose 1 is I. We have mu h plus little o of h to the 1. I'm going to use one of our computational simplifications on this one. We've got 1 minus I minus 1 mu h plus little o of h. In the next line, I've got lambda h, so that's this. And then the e turns into 1 minus lambda h plus little o of h. We have I choose 2, which is 1/2 I minus 1 once you read out the factorials. We have this guy squared, and we showed in one of our computational simplifications last time that that thing I just underlined is equivalent to mu h squared plus little o of h. And finally, we showed last time this sort of computational simplification turns into 1 minus I minus 2 mu h plus little o of h. So, and then plus the rest of the stuff, which is all little o. So now we have to figure out what survives. Like in the first line, we have 1 times I times mu h times 1. And that is order 1 in terms of polynomials in h. So it looks like we have I mu h, and that is not little o. But if we look at like multiplying 1 times I times mu h times this next term, we'll have an h squared in there, and that is little o of h. Or if you multiply the first 3 yellow circles by the little o of h term, it's not like the first 3 yellow circles had an h in the denominator. There was nothing there to counteract the little o of h. So it looks like everything in this line is little o of h, except for that first term that I wrote down. And then in the next line, I have lambda h times 1 times a constant times mu h squared times 1, if you were to start multiplying this out. So that first term has an h cubed in it. And if you go through this, you can convince yourself that all terms in here have h cubed or higher exponents, and all the rest are little o of h. So if this was on the exam, I would say, please write out one of these or something like that. Like, so for example, lambda h times times negative lambda h, like multiply this by this and this, 1/2 I minus 1 times, so it'll be clear. You'll get to see it on the review problems, but you won't have to argue for each and every one of these. But I would also like to make sure you know how to argue for it, and you're not just tacking a little o of h onto the end of everything. But we were looking for the form mu I h because we are decreasing the population size by 1. So this is a death. And the death rate was what was in front of the h. So this is where mu I is defined to be I mu. And that makes sense because each individual in the population, I claim, is dying after an exponential amount of time with rate mu, and they are racing. So the first death is the minimum of a bunch of exponentials, and the minimum of I exponentials with rate mu is exponential with rate I times mu. Yeah, so there are 4 things in this definition, and we showed this one, and we peeled out the birth rates and the death rates, and we do need to show one more. But in the interest of time, I'm not going to do that. I'm going to move on from this example. But yeah, it's not complete until you've shown 3 out of 4 of those probabilities. I'm just going to make a note of that. Need to show one more of the 4 probabilities that we used in defining the birth and death process. Okay, so we keep talking about transitioning in a tiny, tiny time interval. This is an infinitesimal rate of transition. We're going to relate this now to derivatives, and we're going to give those rates special names. So I want to talk for a moment about infinitesimal transition probabilities. Actually, we have been talking about them, but I want to formalize a few things. So this only makes sense for a small h. So I'm going to say as h gets really small and goes down to 0. The probability of moving from I to j in h units of time, that's our new notation for a continuous time chain, is, for the birth and death process, is lambda I h plus little o of h. If j is I plus 1, it's mu I h plus little o of h. If j is I minus 1, I'm really stating the same thing I did in the definition of birth and death, but from a slightly different viewpoint. Before I had K's over here where they represented one birth or one death, K equals 1, K equals -1. And now I'm talking about moving from a state I to another state. In a tiny interval of time, we can only move up by 1 or down by 1 or stay flat. And we are going to stay flat with the rest of the probability, 1 minus lambda I plus mu I h plus little o of h when j is I, and the rest of the probability when I'll just say otherwise. So all we just did now is write out a transition probability for a tiny h. And we want to be able to figure out what the transition probabilities are for any time period. So now what is the probability I move from I to j in t units of time, where t is arbitrarily large? We're a ways away from that, but I want to rewrite this first in a more compact way. So I'm going to write this as Pij of h is a delta ij, which I'm about to define, give me a moment, plus a qij plus little o of h, where delta ij is defined to be 1 or 0. It's going to be 1 if j equals I and 0 otherwise known as a Kronecker delta, if you've used that term. And so this was just a slick way of writing out that thing above, not piecewise. And the Q's are what we're going to like hone in on right now. They consist of like a lambda IH or a mu IH or a negative lambda I plus mu I. And these are infinitesimal transition rates for the probabilities. I will write that down eventually. But first, before going on, note that the probability of going from I to j in 0 units of time, if you're not moving, you can't go from I to j unless j is I. So this is 1 if j is equal to I and it's 0 otherwise. So this is the same thing as that delta. So now we have the probability of going from I to j in a tiny time interval can be written as the probability of going from I to j in 0 units of time plus this qij plus something that is little o of h. And we're going to be able to do this sort of thing for many continuous time processes on a discrete state space, even if it's not a birth and death process. So if you have a process that can instantaneously jump from state I to state I plus 7 with some rate, then we can talk about, you know what, I'll get there when I get there. This is more general, though, than a birth and death process. And check this out. I want to solve for qij. I'm going to move some things around and divide by h. This is pijh minus pij0 over h plus a little o of h term over h. Now, if you're thinking this plus should be a minus, yeah, you're right. But it's little o of h stuff. So usually we just make it all plus. But that is literally a minus. And the QIJs are supposed to be those rates like the lambda i's and the mu i's, and those are constant in time. And we take those to build to a probability that's not constant in time. So there's no h in here. So that's weird. But the QIJ is the limit as h goes to 0 of this thing. This is the limit as h goes to 0 of this bigger expression. The first thing gives you the derivative of Pij, so there's a prime for the derivative at 0, and the second thing goes away. So we store the Qij in what is known as a generator matrix. It's going to be called Q, not to be confused with the Q matrix problems we did. And so this is filled with like Q00, Q01, Q02, etc., Q10, Q11, Q12, etc., etc., etc. These are not probabilities, though. In fact, some of them are negative. For our birth and death process, Qi, I plus 1, is the rate of transitioning up 1, and this is lambda I. And for the birth and death process, Qi, I minus 1 is the rate of transitioning down by 1, and that is the death rate. Qii, if you look at how we define this thing with the delta and compare this to the birth and death process definition, the Qii is this coefficient, negative and all. So negative lambda I plus mu I. So this is a general generator matrix. And then on the side here, I have like specific stuff for a birth and death process. So that's separate, like for a birth and death process. And then the other Qij's are 0 for other j. And they sum to 0, and they always will. So my claim here is that the rows of the generator matrix sum to 0. It's not a probability matrix where they sum to 1. And let's show this. So I am going to sum up Qij over all j in the state space, or j equals 0 to infinity. And this is I'm going to go back to before we took the limit. So this is the sum over all j of the limit as h goes down to 0 of Pijh minus Pij0 over h plus little o of h over h. And this is the limit as h goes down to 0 of Pijh minus Pij0 over h. So I moved the limit across, and I took the limit of this part, which is 0, and I left the other one for now. So now I'm going to interchange the limit and the sum Pij. And so we'll take this sum in here. And we have the limit as h goes to 0 of the sum over j of Pijh minus the sum over j of Pij0 over h. So this first term is 1, because that's the probability of transitioning from I to j in h units of time summed over all j, and you have to go somewhere. The second sum is also 1, and what it is these terms are zeros, except when j hits I. So that sum looks like 0 plus 0 plus 0 plus 0, and then there's a 1 somewhere in there, and the rest are all 0. So both of those circles, those sums are 1. So it's the limit of 0, which is 0. So we started with summing over everything in the ith row of the generator matrix and showed that it sums to 0. Okay, generator matrices are the key to these continuous time Markov chains. We're going to use them in place of the probability transition matrix, because the probability transition matrix, you'll recall, if we use the sort of bold P, it depends on time t, and we're going to have have a different matrix depending on the time. But if we translate everything to this sort of derivative of the p's, these infinitesimal transition probabilities, and work with q's, it's going to be a lot easier. Case in point, the Kolmogorov forward equation. Last time we had the Chapman-Kolmogorov equation, and that gave us that the probability of going from I to j in s plus t units of time can be written as the sum over all k in the state space of going from I to k in s units of time times the probability of going from k to j in the remaining t units of time. So I'm going to take a derivative with respect to t. And so I get the derivative with respect to t, pij s plus t, and the derivative on the right-hand side can come through the sum. And the first term in this, or the first part of that summand, does not even have a t. So the derivative can come all the way through to pkj of t. Okay, so this is, let me write this with primes. I think it'll be a little easier. So pij prime s plus t. That is a derivative. It's the prime is representing a derivative with respect to t. Well, actually, pij has an argument. So the derivative has been taken and s plus t is plugged in to that derivative. This is the sum over k of piks and then pkj prime t. So now I'm going to plug in t equals 0. And on the left side, I get pij prime of s equals the sum over k of piks. And then I don't know if I need to give this another line. I'll write it out. Pkj prime of 0. But this is the same thing as qkj. We showed that qij was the derivative of pij evaluated at 0. So this is the ij entry of the matrix P of S. These are terms across the ith row of P of S, and these are terms down the jth column of Q. And this equation has to hold for all I and j in the state space. So what we have just shown is that P prime of S as a matrix is equal to P of S as a matrix times the generator matrix. This is known as Kolmogorov's forward equation. There's a backward equation coming, and I cannot give you a good, I've been working on this my whole adult life, why one is forward and why one is backward. And the closest I can get to it is the role of these equations in a different area, stochastic differential equations. So this is the so-called Kolmogorov forward equation, and I could use any argument here, any letter. So I am going to rewrite this with a t in it, just so there's no confusion later. I could put any letter I want in there. And this is Kolmogorov's forward equation. So how did we get it? We started with the Chapman-Kolmogorov equation. We took a derivative with respect to t, and we plugged in t equals 0. We could have done that whole thing sort of in reverse. So if we start with the Chapman-Kolmogorov equation and take the derivative with respect to s, and then plug s equals 0 in, then what's going to happen is we're going to show that the matrix P prime of t is the generator matrix Q times P of t. So I left all the detail out, but it's exactly what we did before, just interchanging the role of S and T. the q's will end up on the other side. So yeah, this is Kolmogorov's backward equation. And these will also be on the cheat sheet if you need them. Again, the review problems for the exam will tell you what to expect. So we're going to use these equations. So we've got transition probabilities in tiny, tiny, infinitesimally small intervals of time. Those are the Pij of h as h goes to 0. And those coefficients on those expressions go into Q. But now we're talking about finding probabilities for an arbitrary length of time t. We have a differential equation. It's a matrix vector differential equation, but in some cases, in most cases, this is almost impossible to solve. But in theory, you should be able to solve these differential equations in the two boxes to find P of t. Like to solve for it and find P of t, we're going to do an example after spring break. But the little h thing gives us the rates that go into Q, and this is what translates it back to any arbitrary time interval. But let's do something a little more fun than that. That's tedious and it's actually pretty darn fun. But I would like to get something else out of the way first, and that is stationarity and limiting distributions for continuous time Markov chains on a discrete state space. So we talked about how a Poisson process isn't going to have anything interesting for a stationary or limiting distribution. It doesn't have a stationary distribution because it just keeps going up. But with the death in the process, maybe we can find some balance for our population and talk about the long run probability of there being exactly 100 people in our population. So stationary and limiting distributions, or let me say, sorry, if you wrote that behavior of continuous time Markov chains on a discrete state space. This is actually simpler than it was when we had discrete time. And the reason is there's no such thing as periodicity to mess this up anymore. So remember my failed Marvin the rat problem that didn't have a stationary distribution? Well, it did, but its limiting distribution was not the same. And that's because there was periodicity, because leaving room 1, he can only come back in an even number of steps. There's no such thing as periodicity when there's no such thing as one time step. One time is just continuous. So I think this is actually easier. We're going to call it pi again to denote the entire distribution, or pi I to denote the probability of being in state I when you're in the stationary mode. So we're going to use that same notation. And so before, meaning discrete time, the stationary equation was pi j equals the sum over I of pi I Pij, or we have it in matrix form. And now in continuous time, it does still make sense to use like pi sub I, pi sub j, because the state space is discrete. And the stationary equation is pi j equals the sum over I of pi I Pij of t. And this is something that has to hold for all times t greater than or equal to 0. So it just looks the same, but the Pij depends on time. And so adding to the definition of the stationary equation, we need it to hold for all time. And the vector matrix version of this would be a row vector of pi's equals a row vector of pi's multiplied on the right by the transition matrix at time t. As I was just saying, it is really, really hard to find the probabilities of moving from any state to any other state in an arbitrary amount of time that is not negligible. We define things in terms of tiny, tiny intervals, and we have not found yet any probability of moving from one state to another in an amount of time that's not negligible. To do that, we'd have to solve one of the Kolmogorov equations, and we will after the break. But for now, I've got a really cute theorem for you. And it is how to identify a stationary distribution without ever looking at the probability transition matrix. So I'm going to call this CTMC for continuous time Markov chains dash T1 for theorem 1, just so I can refer to it later. And so the setup is continuous time discrete state space, and the vector of pi's is a stationary distribution if and only if pi times q, which is going to be a 1 by the size of the state space, is the zero vector. So we're going to prove this. It's not that hard. And we're going to use this to solve for pi as opposed to this. Because in order to solve this one, we need to be able to find this, and that's really hard. The Q matrix for a birth and death process is mostly filled with zeros. It has something above the diagonal and below the diagonal and on the diagonal, and the rest are zeros. And we're going to use that to find a formula that will work for any birth and death process where you won't have to rederive it over and over again. So let's prove this. So first, I'm going to go in the forward direction. I'm going to assume that pi is stationary for the chain. Okay, so I'm going to start off using Kolmogorov forward or backward. Forward or backward. I can't remember which is forward or backward. I think this is forward. So Kolmogorov, the forward equation, is the one that says that the matrix P prime of T. By the way, what that means is entry-wise derivatives. I never mentioned that before. We concluded this. Well, actually, we concluded this from this. This is the derivative of the ijth entry. So what I mean when I put the prime on the whole matrix is entry-wise derivatives. Okay, so the forward equation is the one that has the q on the right side. So P times Q. You do not have to remember that. It will be given to you if you need it on the exam. Or if we just write the ijth entry of this, this is saying the probability of going from I to j prime, the derivative, at time t can be written as the sum over k of pi k of t times q k of j. So that's just the ijth entry for both sides of that equation. I'm going to multiply both sides by pi I and sum over I. And sum over I. So on the left side, I get the sum over I of pi I p I j prime of t. On the right side, I get the sum over I of pi I, the sum over k of p I k of t, q k of j. And on the left side, this I can pull the derivative out. So this is the derivative with respect to t of the sum over I of pi I pij of t. On the right side, if I interchange the order of summing and if I interchange the order of the sums, then I get the sum over I of pi I pik of t, oops, and then this q, kj, which can be pulled out of the I sum. And because we're assuming we have something stationary, the thing in the parentheses on the right-hand side is pi k. So this is the stationary equation, but we have a k where the j was. So this is since pi is stationary. And again, we defined pi j as the sum over I of pi I, pij of t. But here I had pik. So that's why rather than getting the pi j, I get a pi k. On the left side, I have the derivative with respect to t of, again using stationarity, pi j. On the right side, I've got this thing. But those probabilities are constant in time. They don't depend on t. So I have 0 equals the sum over k of pi k q kj. And this is us getting the jth entry of the vector, the row vector of pi's times the matrix of q's. So this is the jth entry of the pi vector times the q matrix. This equation holds for all j in the state space. So I can just say that the vector pi times the matrix q gives us the 0 vector, which is what I was trying to show in this theorem. The forward direction, pi being stationary, gave us this result, which I don't think is that interesting. I think the other direction is interesting. If you can show, if you have a q, and if you could find a vector of pi's that satisfies this, then you necessarily have a stationary distribution. So this is how I would go for a stationary distribution in continuous time. I would try to write down that generator matrix and try to solve this equation. So let's show that this goes in reverse. So suppose now that we have that pi times q is the 0 vector. Do I care about pulling one of these out? I guess not. Let me start with, let's look at for any j. Consider kind of thinking about, I know this is a little unmotivated, but kind of thinking about how the other part of the proof went. Let's consider the derivative with respect to t of the sum over I of pi I pij of t. This is the sum, pulling the derivative in, of pi I pij prime of t. This is the jth entry of the vector of pi's times the derivative of the transition probability matrix. So by this, I mean the jth entry. I guess I could have written, this is the jth entry of that. But by the Kolmogorov backward equation, we know that that derivative p prime of t is q times p of t. So this is pi times q of p of t, the jth element. So yeah, when I'm saying like a j, this is the jth element of a. Well, a looks like a matrix, but it's a vector. Okay, so we're assuming in this direction that pi times q is 0. So this is 0. So this is 0. The jth element of that is 0. And I started with the derivative of this. So what this gives us, being equal to 0, this implies that the sum over I of pi I pij of t is constant in t, and this holds for all j in the state space. because its derivative is 0. Its derivative with respect to t. And let me go back to my newly formed notation. This is saying that the vector pi times the matrix P, if you look at the jth entry, this is a constant. And it's for all, well, for each j. So it's constant for all t for each j. It doesn't have to be the same as you change j. So this should be equal to whatever it is when time is 0. And that has to hold for all j. So what this is saying is that if you look at the vector times the matrix, this is going to be the same thing as the vector times the matrix with any time I want to plug in. And I'm going to plug in time 0. But when you plug in 0, this is full of transition probabilities of moving from I to j in 0 units of time. And you're not moving anywhere unless j is equal to I. So this is the identity matrix. Which means we just get pi out of this. And showing that this is equal to this is showing stationarity. So we're getting that from assuming that this pi times q is 0. Super cool. What can I clear up? All right. So the last thing I can do today is about finding a formula for pi for a birth and death process. Everything we were just talking about doesn't have to be a birth and death process, just a continuous time chain on a discrete state space. But for a birth and death process, I kind of hate to do this, but it's going to allow me to make your homework more interesting and fun for you. Otherwise, I can only ask some very limited theoretical things. So I am going to start off with a formula that we're then going to derive and continue deriving after spring break. So if we have a birth and death process with birth and death rates, lambda I and mu I, respectively, I claim that under some mild conditions on these rates, that a limit always exists, a limiting distribution, as long as it's not blowing up like birth rates much higher than death rates, and that it's stationary. And we are going to use the Kolmogorov equations in order to find that the long run equilibrium probability of having n people in the population is equal to the product lambda naught, lambda 1 up through lambda n minus 1 over the product mu1, mu2 up through mu n times pi 0. That kills me to write that. I really wanted us to discover it through a derivation. We will derive it next time. But let's do a quick example. Okay, and then we're out. Oh, really quick. Maybe I can't do this. Okay, I was going to motivate this with a special queuing network that I was going to describe, but let me just, to make this fast, say, suppose we have constant birth and death rates. So the lambda i's are all lambda and the mu i's are all mu. Then we get pi n we get n lambdas over n mu's times pi 0. If we believe this formula. And so to find pi 0, note that we need these to sum up to 1. So 1 is going to be the sum as n goes from 0 to infinity of the pi n. And by the way, this formula holds even when n is 0. So this is the sum as n goes from 0 to infinity of lambda over mu to the n times pi 0. Pull the pi 0 out. The sum n goes from 0 to infinity, lambda over mu. We have a geometric sum. And if lambda is less than mu, then this converges to 1 over 1 minus lambda over mu. That's a times, that's multiplied. And so this is equal to 1. So what we have shown is that pi 0 is 1 minus lambda over mu, and then pi n is lambda over mu to the n times pi 0, as long as lambda is less than mu. Oh, that was awful. So I wanted us to discover this, and I wanted to motivate this problem as a real life problem. But right now, some computation, because finding stationary distributions for birth and death processes as an exercise, like on homework or something, super easy. You have a formula and you plug in birth rates and death rates. And then to solve for the pi 0, you want to make sure that all the pi's sum to 1. So yeah, we'll talk more about that on Monday after spring break. So next time, Markov processes.